Welcome back to the first Algebraic Graph Theory seminar of the year. Today we have Ada Chan from York University, who is going to be telling us about complex Hadamard diagonalizable graphs. So I will let her take it away. Thanks.
Thank you, Max. Thank you everyone for coming. I know the term hasn't started for most of you, and I hope you all have a good restful break in the last couple of weeks. So in this talk, I mostly just want to tell you the story about basically my encounters with these graphs called complex Hadamard diagonalizable graphs in the last few years. Okay, so there are three parts to this talk. So the work is basically an extension of work done by Barik, Sean, and Steve on Hadamard diagonalizable graphs. So when I look at this paper, they mentioned how a lot of results in algebraic graph theory are looking at like the structure of a graph if you put restriction on eigenvalues. So in this paper, they say, well, why don't we put some restriction on the eigenvectors and then look at the structure of the graph? And I thought that's a pretty neat idea. Okay. And then I was kind of further motivated by this paper where Nathaniel, Steve, Sarah, Rebecca, and Xiaohong, they look at perfect state transfer in the graphs that are diagonalizable by Hadamard matrices. And when I look at that paper, I go, of course, because these graphs are actually good candidates for graphs to have perfect state transfer in the continuous time quantum walk. And I'll talk about a general version called fractional revival in this talk, and I hope to convince you why I think these graphs will be good candidates. So that's the second part of this talk. Okay. And then the third part is something that I worked on many, many years ago as a PhD student. And this part, I haven't gotten any progress, but it's really the main kind of a reason why I choose to talk about this topic today, because I'm hoping to get more people interested and work with me on that problem. So I'll talk about this part towards the end of the talk. Okay. All right. So complex Hadamard diagonalizable graphs. So I was really motivated to look at the Hadamard diagonalizable graphs because of the quantum walk and also because of the type 2 matrix and what we call the Nomura algebra of type 2 matrices. Hadamard matrices are examples of type 2 matrices. So there's a problem that Chris and we talked about many years ago about the Nomura algebra of Hadamard matrices that's still open. And so that is like my main motivation. So I remember like in 2017 in the ILS meeting at Ames, I was talking to Sean, Steve, Sarah, Shala, and Jeffian, and basically I was just kind of asking them about these graphs, Hadamard diagonalizable graphs, and I really wanted to learn more about these graphs. And I still remember us kind of standing around in a circle, and I was telling them about the type 2 matrices, and also asking them about these graphs and the perfect state transfer. And so they basically, I told them that I really want to learn about this topic, and they kindly indulged me, and that is basically the start of this project. Okay, so first let me define complex Hadamard matrix. So a complex Hadamard matrix is a square matrix, and all of its entries have absolute value 1, so the entries are complex numbers, and then we have this condition here. This condition here basically says that the inverse of this matrix is 1 over n times the conjugate transpose of the matrix itself. And we know examples of matrix with these that satisfy these conditions. For example, Hadamard matrices. So for Hadamard matrices, H inverse is 1 over n times X transpose. Now, Hadamard matrices are basically complex Hadamard matrix with entries plus or minus 1 only. Okay, so then we don't have to take the complex conjugate. Okay. Another class of complex Hadamard matrix that we will talk about today is called a Turin Hadamard matrix. So these are complex Hadamard matrix. So they satisfy the 2 conditions in the definition with entries plus or minus 1 and plus or minus I. So if you look at the literature, actually at the beginning when people start talking about complex Hadamard matrices, sometimes when they say the papers on complex Hadamard matrices, but they're really talking about Turin Hadamard matrix. Now then, another class of examples is basically what we call Butson type Hadamard matrix. These are complex Hadamard matrix where the entries are some qth root of unity. Okay, Q doesn't have to be a prime. For example, if you look at the character table of the group set Q, the cyclic group set Q, then we would have basically a Q Butson type Hadamard matrix. Okay, so these are some examples. Now, if I give you a complex Hadamard matrix, then I can form a new one by, say, just permuting rows and columns of my complex Hadamard matrix. Or I can scale some rows and scale some columns using a scalar with absolute value 1. And after performing this operation, I would have a new complex Hadamard matrix. But then we consider these two complex Hadamard matrices are equivalent. Okay, they are basically, we think of them as almost like the same. Okay? Now, for example, if you look at all 4x4 complex Hadamard matrix, then we know that they are equivalent to a matrix of this form. Okay, so the first two columns and first two rows are kind of almost like a Hadamard matrix. And then the only kind of thing that you can vary is this little 2x2 block in the bottom right corner. And it will work if you pick any gamma with absolute value 1. Okay, so you have infinitely many complex 4x4 complex Hadamard matrix. Okay, so what is a complex Hadamard diagonalizable graph? So we're just generalizing the definition in the original paper by Barik, Sean, and Steve. And so we say that a graph is complex Hadamard diagonalizable if you can find a complex Hadamard matrix for which the columns of this matrix are all eigenvectors of the Laplacian matrix of the graph. Okay, so or in other words, I will have this equation here. Okay, so this diagonal matrix lambda is the matrix that stores the eigenvalues in its diagonal entries. So a simple example, if you look at the Laplacian matrix of the complete graph K4, it is just 4 times I minus J, the matrix of all ones. Okay, so if I multiply the Laplacian matrix of this graph to basically any 4x4 complex Hadamard matrix of this form, okay, then it's easy to see that the green column, the vector of all ones, is an eigenvector with eigenvalue 0. And then the reddish columns, the 3 columns, they are eigenvectors of the Laplacian matrix with eigenvalue 4. So this is basically our matrix that stores the eigenvalue. This is the matrix lambda. And so we can see that for this example, this Laplacian matrix of the complete graph is diagonalizable by any 4x4 complex Hadamard matrix of this form. Okay. And here is, we have an interesting example. Okay. So let's pick a finite abelian group. Okay. Let's say we have n elements. And let's pick a Cayley graph with connection set C. Then the Laplacian matrix, well, the Cayley graph is regular, so it has degree, which is the size of the connection set. So the Laplacian matrix is C times the size of C times the identity matrix minus the adjacency matrix. Now we know that the characters of this group are eigenvectors of the adjacency matrix. So the Laplacian matrix being basically a multiple of I minus A, again would have the characters of the group being eigenvectors. So if I write down this matrix H, which have the columns being the characters, or which is just the transpose of the character table of our group, then the Laplacian of the graph is diagonalizable by H. Now conversely, basically what we do is we can take a regular representation of the group. Okay, so in this, we can represent each element using a permutation matrix. Okay, so we have n permutation matrices that represent our group elements, and all these matrices are diagonalizable by this matrix H. Okay, so then well, we have a space spanned by n permutation matrices, and this space would basically contain all possible matrices that are diagonalizable by the matrix H. So what happens is if I have a graph that is diagonalizable by H, then this graph would basically have to be in this span, or it's a linear combination of these permutation matrices. So basically we're saying that if I have any graph that is diagonalizable by this matrix H, which is the transpose of the character table, then that graph has to be a Cayley graph. So we talk about cube-like graphs. So this here, this is a Sylvester construction of a Hadamard matrix. So you just take the 2 by 2 Hadamard matrix and take Kronecker product of itself. And so this is the character table of the group set 2 to the m. Okay. So then a graph is diagonalizable by this matrix if and only if it's a Cayley graph of the group set 2 to the m, or we call it the cube-like graph. Okay, so when I look at the first paper, the first question that came to my mind is, well, why Laplacian? Because we usually work with the adjacency matrix. It seems a strange choice to me. Why do they want to work with Laplacian? And it turns out that I think it's a very clever choice because with the Laplacian matrix, if G is connected, then we know that we always have the eigenvalue 0. Okay, and we always have the eigenvector, which is the vector of all ones. So let's suppose I have a graph and its Laplacian matrix is diagonalizable by some complex Hadamard matrix. And let's say in this complex Hadamard matrix, none of the columns is a vector of all ones. Okay, then that would imply that the graph is not connected, because I know that the Laplacian matrix of any graph would have 0 as an eigenvalue. And we also know that the eigenvector corresponding to the eigenvalue 0, the entries are always constant on the components. Okay? So if I have the Laplacian matrix of some graph, and it's diagonalizable by the matrix, some complex Hadamard matrix H, okay? And if I pick a column, let's say the first column, it corresponds to the eigenvalue 0, okay? Then I know that the entries will be constant on the components. So let's say we have 3 components. Okay, so let's say I have entries alpha, beta, and gamma here. Okay, then what I can do is I can scale the rows. So I'm going to multiply 1 over alpha to the first group of rows, 1 over beta, and 1 over gamma. I can scale the rows of this matrix. Okay, now because basically these partition of rows correspond to components in the graph. Okay, so after scaling the rows of this matrix, each column vector of this matrix will remain an eigenvector of the original graph, of the Laplacian of the original graph. So basically, I am free to scale the rows and get a new complex Hadamard matrix that diagonalizes the Laplacian of my graph. So by looking at Laplacian matrix instead of adjacency matrix, I can assume that in my complex Hadamard matrix, I always have the first column being or at least one column being the vector of all ones. I can permute it to make it the first column. Okay, and this column would correspond to the eigenvalue 0. Okay. Now, since the columns are eigenvector, I am free to scale each column. So I can also make the first row having only entries 1. So I can assume that my complex Hadamard matrix is a defaced, so having ones in the first column and ones in the first row, complex Hadamard matrix. Okay. Now, if you're looking at real Hadamard matrix, then we say it's normalized instead of using the word defaced. They basically mean that we have ones in the first row and only ones in the first column. Okay, so this is what we can assume that we can work on. Okay, so let's see what we can say about these matrices. Now, given a complex Hadamard matrix H, if I just want to write down basically the set of all matrices diagonalizable by H, it's actually very easy, because all I have to do is to take each column and compute this outer product, okay? And then that will give me a basis and take the span. So I have an n-dimensional space. But we are asking for graphs that are in this space. So we're asking for, if you think of adjacency matrix, it will be a 0, 1 matrix. If you think of a Laplacian matrix, then it will be basically you have this diagonal, which are the degrees, minus the adjacency matrix. So we're asking for matrices that has a very kind of a special structure in this set here, in this space here. So that is a bit more difficult. But there's something that is very quick that we can say given this basis for the space. For example, if you sum these HI transpose over all J, then you would get the identity matrix. Okay, so the identity matrix is in the set. We assume that the complex Hadamard matrix is defaced. So we say that we assume that the first column is the vector of all ones. So if you look at H1 conjugate transpose, then we get the matrix J, matrix of all ones. Okay. So then that immediately tells me that no matter what H is, because we know that the Laplacian of the complete graph is n times I minus j, okay? And we know that I and j is in this space. So then the Laplacian matrix of the complete graph is always in the space S. So we know that no matter which complex Hadamard matrix we're dealing with, as long as it's defaced, then the complete graph is diagonalizable by H. Okay, so it's something quick. Now, if we have, say, one column in this matrix with only entries plus or minus 1. Okay, so I just kind of group them so that I have got a +1 on top and -1 at the bottom. Then HJ conjugate transpose will be this matrix here. Okay, so we know that the matrix of all ones in the space, we know that I is in this space. And now we have this matrix in this space. So basically we can recover the Laplacian matrix of the complete bipartite graph. So the complete bipartite graph with half the vertices on one side is diagonalizable by the complex Hadamard matrix, as long as we can find one column with entries only plus or minus 1. Okay. So recently, Jane and there's a whole group of people, so Xiaohong's also in this group, they looked at the graphs that are Hadamard diagonalizable, so only real Hadamard matrices, okay, and they look at size 36, but they show that when n is congruent to 4 mod 8, then basically, so we look at Kn, the complete bipartite graph, okay, and these two are complement of those two graphs, and these are the only graphs that are Hadamard diagonalizable. So this is real Hadamard matrices, not complex Hadamard matrices. Okay, so what more can we say? Okay. So the space of matrices that are diagonalizable by H, it's given here. Okay, so if you look at each of these matrix HJ conjugate transpose and look at the diagonal entries, so I'm looking at the UU entry here. So basically, I'm looking at the U entry of HJ multiplied to the conjugate of basically the same number itself. So I'm really looking at the UJ entry of my original matrix. Okay, I take the absolute value square. Now, because H is a complex Hadamard matrix, and each entry has absolute value 1. So then I would know that the matrix HK conjugate transpose would have basically, if you look at the diagonal, we'll see basically all ones. So it's constant diagonal. All right. So so basically, if you say I have a graph that is diagonalizable by H, then L of the Laplacian of this graph is in this set S. Okay, that means that the Laplacian matrix has constant diagonal entries. Okay, so a quick consequence is that any graph that is diagonalizable by H is a regular graph. All right, so then since we have regular graph, let's say the valency is K, okay, then I can write the adjacency matrix as basically K times I minus L. So this is telling me that if the Laplacian matrix of a graph is diagonalizable by H, then so it's its adjacency matrix. All right, so this is a question that bothered me a little bit for a while, because remember before I say my first question is why Laplacian, and Laplacian is Laplacian is a clever choice because with Laplacian matrix we can assume that the Hadamard matrix, the complex Hadamard matrix, is defaced, meaning that I have this kind of column of ones, and then now I know that L of G, like the graph is regular, so then adjacency matrix, it's also diagonalizable by the same complex Hadamard matrix. And so it took me a while, and I keep thinking that, okay, what happened to, is it possible to have a graph that is not regular, but its adjacency matrix is diagonalizable by some complex Hadamard matrix? Now that complex Hadamard matrix might not be defaced. Okay? And so is it possible? So this is a question that I kind of brought up. And and Sarah and Steve, they come up with a clever argument. Okay, basically they look at the parent eigenvector of the adjacency matrix, and they applied a triangular inequality argument to compare the spectral radius of the graph versus the row sum of the adjacency matrix, and they show that they have to be equal. Okay? So what happens is if I have adjacency matrix of a graph that is diagonalizable by some complex Hadamard matrix, okay, it might not be defaced, but then they can show that then the graph has to be regular. Okay? And because the graph is regular, its Laplacian is just k times I minus a. So then its Laplacian matrix, it's also diagonalizable by H. Okay, so this is basically telling us that it doesn't really matter if you talk about adjacency matrix or Laplacian matrix when you look at graphs that are diagonalizable by G, by H, by complex Hadamard matrix. Okay, so here's a quick observation. So if I have a bunch of matrices, the M matrices, they're diagonalizable by a complex Hadamard matrix H1, and then another bunch of matrices N, the N matrices, they're diagonalizable by another complex Hadamard matrix H2. Then basically the tensor products are diagonalizable by H1 tensor H2, and so is any linear combination of the tensor product. Okay, so this quick observation is telling us that has covered basically a lot of our graph products. So we have the union, we have the join, double cover, Cartesian, NEPS, and merge. Merge is a product that Nathaniel et al. Talked about in the second paper that I showed. And so what happened is basically these products and also the complete graph and the complete bipolar graph and complement, which give us all the graphs that are diagonalizable by a Turin Hadamard matrix of size less than or equal to 8. Okay, so what more can we say about these graphs? Okay. So again, we start with a complex Hadamard matrices. I'm using H1 up to Hn to denote its columns, and then we can write down the space of matrices diagonalizable by these columns. Okay, so as I said before, it doesn't matter if we look at A and G. So let's just use A here, and I'm writing down a spectral decomposition of A, which is also basically the projection matrices onto the eigenspace is the same as the ones for the Laplacian. Okay. Now we know that these matrices all have constant diagonal. So this is telling us that any power of A would have constant diagonal. Okay, so basically any two vertices will have the same walk generating function. It's also telling us that all these projection matrices, all these principal idempotents, ERs, would have constant diagonal. And then so this is basically equivalent to saying any two vertices, A and B, are cospectral. So if a graph is complex Hadamard diagonalizable, then basically all the vertices are cospectral with each other. So this is another quick thing that we can say about these graphs. Now I'm going to throw in an extra condition. So suppose we have a column that has only entries plus or minus 1 and plus or minus I. Okay, so this is something extra, but I'm thinking about the Turin Hadamard matrix or the real Hadamard matrix when I throw in this condition. So we look at that column, and then we can partition the vertices of the graph according to the entries in this column. So if the entries are plus 1, then I throw into the set R plus. If the entries is -1, I'll throw in the set R minus. R stands for real. If the entries are I, then I throw in the set I, imaginary, plus, and then the rest will be in I minus. So I have 4 sets. It partitions the vertices of the graph. Okay. Now, and on this slide, I pick a vertex U in the R plus set in the blue circle, the light blue circle. And then I want to compute the U entry of this equation here. Okay, so I'm using R plus U here to denote the number of neighbors of U in the blue circle. R minus U will be the number of neighbors of U in this circle here. And then I will have I plus U and I minus U. So then these 4 numbers, when you add them together, it'll be the valency of the graph. So we have the first equation here. Now, if I look at the U entry of this equation here, so this is L times xj equals to lambda j times xj. So lambda j is the eigenvalue. Then I get the equation here. So you just have to basically unpack the equation. And a quick thing that we can notice is that if you look at the imaginary part of both sides, because lambda j is a real number, so that will immediately tell me that this part is 0, okay? Or the 2i numbers are equal. And then if you compare the real part, then I would get the second equation here. Okay? So you just have to stare at it for maybe like a few seconds, and you see that combining these equations, we get this equation here. So what is this saying? This is saying that R minus U plus I U minus is lambda j divided by 2. Okay? And this is the number of edges or number of neighbors that the vertex U has on the red side, on the right-hand side. Okay, so this is basically what we have seen. So pick any vertex U in the R plus set, then it would have exactly lambda j over 2 neighbors on the red side, and it would have basically k minus lambda j over 2 neighbors on the blue side. Okay? You do the same thing for a vertex in the I plus set, any vertex in the R minus set, and any vertex in the I minus set. Okay, so basically the same analysis. So I'm going to skip it. And what we see is that if the jth column of the complex Hadamard matrix has entries plus or minus 1 and plus or minus I only, then if we partition the graph, so we basically throw in the vertices that have entry plus 1 and plus I on the right-hand side, on the blue side, and then you throw in the negative 1 and negative I entries, so those vertices on the right, on the right side, on the red side, then we would have an equitable partition. Okay. And then this is the quotient matrix. So this is telling us that the eigenvalue that corresponds to any columns that have only plus or minus 1 or plus or minus I entries, they have to be even integers. Okay, so this is another kind of consequence that we have. Okay. And then notice that we have a very neat edge cut here. Okay. In this edge cut, we have exactly half the vertices in the blue side and exactly half of the vertices on the red side. Okay. So we look at this edge cut and we compute the Shear constant of this set here. Okay. So the Shear constant is basically this ratio here. On the top, you're looking at the size of your edge cut. And then at the bottom, in the denominator, you're looking at the minimum of the total degree on each side. Now we have n over 2 vertices, okay, and each vertex has exactly on the blue side, and each vertex has exactly lambda j over 2 neighbors on the red side. So the edge cut will have size basically n times lambda j divided by 4. And then we have n over 2 vertices on each side, and each vertex has degree k. So then in the denominator, we have kn divided by 2. Okay, so then the Shear constant for the blue set is lambda j divided by 2k. Okay. Now the Shear constant of the graph is basically you go over all possible proper subset of the vertex set, and you compute the Shear constant of the set, and then we take the minimum. So we know that the Shear constant of the graph is at most lambda j divided by 2k. Now, so let's kind of say focus on the Turing type Hadamard matrix. So every columns would have plus or minus 1, plus or minus I entry. Okay. Well, the first column has only entries 1, so we don't worry about the first column. So I'm going to order the columns or order the lambdas so that the lambda 2 is the second smallest eigenvalue. So this is telling me that the Shear constant of a graph, any graph that is Turing-Hadamard diagonalizable, it's at most lambda 2 divided by 2k. Now, when we talk about Shear constant, there's an equality. And the inequality, it's usually given by the second smallest eigenvalue of the normalized Laplacian matrix of the graph. But because the graph here are k regular, okay, then we know that the normalized Laplacian matrix of the graph is 1 over k times the Laplacian matrix of the graph. Okay. So the second smallest eigenvalue of the normalized Laplacian matrix is basically just lambda 2 divided by k. Okay, so that's why for k regular graph, I'm just writing the Shear inequality in this form in terms of lambda 2. So what we have here is for any graph, the Shear constant, it's bounded below by lambda 2 over 2k. Okay? So then we see that if a graph is diagonalizable by either the Turing-Hadamard matrix, and it also works for real Hadamard matrix, then the lower bound of the Shear inequality is always tight. Okay, so just summarize what we know about these graphs. If a graph G is diagonalizable by a Hadamard matrix, so a real Hadamard matrix or Turing-Hadamard matrix, then we know that we have these equipartitions. So we have 1 for each lambda, except for the first column. So we have n minus 1 different equitable partitions. I call it balanced because in these equipartitions, we always have exactly half of the matrix on half of the vertices on one side, and half on the other side. And we know that all eigenvalues for the Laplacian matrix are even integers. And then we also know that the lower bound in the Shear inequalities is tight. Okay, so for example, if you look at Cayley graphs on set 2 to the m, so then H is Hadamard matrix. Or if you look at Cayley graph of set 4 to the m, then we're talking about Turing type Hadamard matrix, then all these conditions will hold for these Cayley graphs. Okay, so let's move on to the second part of the talk. Let's talk about continuous time quantum walk. Okay, so right. So in this talk, I'm just kind of focused on the Laplacian continuous time quantum walk, and its transition operator is given by given by this matrix, e to the minus ITL. There have been a few talks in the seminar on continuous time quantum walk, so I won't kind of give an introduction to these walks. Okay. So in this talk, we're dealing with regular graphs. So I can write L as k times I minus the adjacency matrix. So what happens is the transition matrix for the Laplacian walk is really a scalar multiple or phase vector times, you can think of this as a Laplacian matrix for the adjacency walk if you replace t by minus t, so you kind of reverse time. Okay, so the transition matrix for K2 is given here. Okay, this is basically the most popular example that we will use in quantum walk. It has a very nice form. Okay. And we say that fractional revival occurs between two vertices A and B at time tau. If so at time tau, if you look at the transition matrix, here E to the A is the characteristic vector. of the vertex A. So here we're looking at the A column of the transition matrix at this time. Then it has only two non-zero entries at the A position and at the B position. Okay, well, I say at most two non-zero entries, alpha and beta. Okay? And we need alpha and beta to satisfy this equation. Okay, and it's a result of U of tau being a unitary matrix. I'm going to throw in an extra condition here. Okay, because if beta is equal to 0, then we're really looking at basically U of tau times EA equals alpha times EA. So B never plays a role. So we say that the walk is periodic at A, and I don't want to look at that. So Xiaohong talked about fractional revival in her talk, and I think she calls this proper fractional revival if beta is non-zero. But I'm just going to assume that beta is non-zero in this talk. So for example, if you look at K2, let's say the first column is indexed by A, the second column is indexed by B. Then if I looked at, let's say at time pi over 3, so then this product here, I'm picking up the first column. Okay. Then I would have, so this is my alpha times EA, plus this is my beta times EB, and alpha and beta are both non-zero. And this is an example of fractional revival. Now, if I look at the time at pi over 2, okay, then cosine pi over 2 is 0. So this is my alpha, and this is my beta. Okay. We still have fractional revival, but this is a special case. So this is a case where alpha is 0. Okay, so this is a case where at this time in the transition matrix, if you look at the A column, then you have exactly one non-zero entry at the vertex B. And when this happens, we say that we have perfect state transfer from A to B at this time, pi over 2. Okay, so let's see what happens to a complex Hadamard diagonalizable graph. Okay, so I'll start with the complex Hadamard diagonalizable graph. Okay. So then I can write the Laplacian matrix as H lambda and H inverse. Okay. Now then I can write the transition matrix of the walk, okay, very easily. I can write it as H times exponential e to the minus IT lambda times H inverse. All right, so then now let's suppose we have fractional revival from A to B at time tau. Okay, so I can rewrite this equation as H e to the minus IT lambda H inverse e to the A equals alpha EA plus beta EB. Okay, I can multiply H inverse to both sides. So what I have is, I can rewrite this as, so I can add H inverse to both sides. Okay. H is a complex Hadamard matrix, so H inverse is 1 over n times the conjugate transpose of H. Okay, so that's how I get this equation here. Now then, if I look at the R entry of both sides, then H star EA is just really the AR entry of the conjugate of H. Okay, so I get this second equation here. Now, let's say R equals 1. So let's just restrict ourselves to the first entry. Okay, so the Hadamard matrix is defaced, meaning that the first column, we assume the first column is the vector of all ones. So we have these numbers being 1. Then the first eigenvalue is 0. So that means that this number here is 1. Okay, so if I focus on R equals 1, then the equation that I get is 1 alpha plus beta equals 1. Okay, so this is what happens when R equals 1. Now this equation holds for all R. Okay, so let's pick any R that is not 1. Okay, so then I'm rewriting this equation over here. And then I divide both sides by the conjugate of the AR entry of H. Okay, and then I get the next equation here. Okay, because the AR entry of H has absolute value 1, so I can rewrite this number here as HAR over HBR. Okay. Okay, so what's happening here? So there's a lot of equation. what's happening here is if you look at the red equation, so I'm just drawing this, I'm drawing the complex plane on a complex plane. If I draw alpha and beta, then they sum up to 1. So I have the triangle, the red triangle here. Okay. But I also know that the square of the absolute value of alpha and beta, they add up to 1. So I know that this red triangle is a right angle triangle. Okay. Now, the equation, let me change it to blue. The equation here tells me that, well, alpha plus beta times this blue number. Now, because H is a complex Hadamard matrix, okay, so all the entries will have absolute value 1. So this number here has absolute value 1. So I'm thinking of taking alpha, okay, and then I'm thinking of taking beta, but maybe I'll rotate beta a bit. So maybe taking beta. So beta times this blue number. Okay, so that would be alpha plus beta times this blue number. Okay, but then the left-hand side of this equation tells me that this number is also like this sum here has absolute value 1. This number is e to the minus I tau lambda r. Okay, so this I would expect this point here. So I would expect this point here to be on the unit circle. And the only way I could have this point here to be on the unit circle is that this number, it's either plus 1 or minus 1. Okay, so either we're talking about alpha plus beta or alpha minus beta. That's the only way that I would have alpha plus beta times a unimodular complex number to be on the unit circle. Okay. So the conclusion is if I have fractional revival at time tau between A and B, then I would need that the AR entry of the complex Hadamard matrix is plus or minus the BR entry. And this has to be true for OR. Okay. So this is saying that, well, if you look at the rth column, okay, so the rth eigenvector, and you look at the A entry and the B entry of the eigenvector, then they have to be either equal or minus 1 times each other. Okay. And then I also would need the eigenvalue to kind of match up to alpha plus or minus beta, depending on what that blue number is. Okay, so I would need these two conditions. Okay, so I'm just going to summarize what we have. So if the Laplacian matrix is diagonalizable by H, then we have fractional revival if and only if these two conditions occurs. So these two conditions are sufficient to give us a fractional revival, but I haven't shown you why. Okay, but it's an if only if condition. Okay, so then we say, okay, we need the first condition to be true. And the first condition is always true if H is a real Hadamard matrix, because the entries are always just plus or minus 1. Okay, and this is the reason why when I look at Nathaniel et al.'s paper, I thought, oh, of course, because if you have a Hadamard matrix, then the first condition always holds. And so Hadamard diagonalizable graphs are actually good candidates, good place to look for graphs with perfect state transfer. Okay, so condition 1 always holds. All right, then and then if I look at these conditions a bit more, okay, condition 1 alone would imply that A and B are cospectral. But when we actually look at that, any graph that is complex Hadamard diagonalizable will have all its vertices being cospectral to each other. But if I just kind of zoom into these condition 1, condition 2, then the cospectrality follows from condition 1. Now, if you look at condition 2, okay, condition 2 is saying that suppose I have 2 columns in my matrix H. Let's say column R and column S, okay? And they correspond to the same eigenvalue. So lambda R equals lambda S. Now, because lambda R equals lambda S, this is telling me that basically either both HR and HS would fall into the first case together, or both HR and HS would fall into the second case together at the same time. Okay, so the second condition is telling me that any 2 eigenvectors within the same eigenspace, okay, would basically fall into one of these two cases. So I cannot have an eigenspace where I would have one eigenvector satisfying the first case, and then another eigenvector satisfying another case. So this condition is basically telling us that if I take the projection onto the eigenspace, then I would have this condition. And this is true for any eigenspace S. Okay, maybe I shouldn't be using S. Let's use J. Okay, so it's telling me that, and then in this case, we say that these two vertices are strongly cospectral. Okay, so when we have this condition happening. Okay, so I was working on this, and then I remember I was staring at a lot of Hadamard matrices, and then I was thinking, okay, I know that condition 1 holds for any real Hadamard matrix. So condition 1 is not an issue. It's condition 2 that is an issue if I want to find graphs with perfect state transfer. And then I was wondering, like, okay, how do I know if two vertices are strongly cospectral if I'm staring at a Hadamard matrix? And then also, how do I know? Oops. Oh, okay, my screen froze. Let's see if this is better. Okay, sorry, excuse me. So I'm going to have to stop the app and restart it. Okay, so let's hope it works. Okay. So and then another question is, if I have a Hadamard matrix, is it even possible to have, say, more than two vertices, okay, that are strongly cospectral with each other? So I was having my sabbatical in 2019 to 2020, and starting in about the fall, Harmony and I started going to Waterloo every week. And the nice thing about going to Waterloo is like there are a lot of people to talk to about these questions. And the nicer thing is, now that they listen to me kind of babbling about these questions, they would come up with answers. So I was asking the folks at Waterloo, like if I have a Hadamard matrix, and if I'm looking at a Hadamard, so just real Hadamard diagonalizable graph, is it possible to have more than two vertices that are pairwise strongly cospectral with each other? And Sophia talked about this in her talk. So Sophia's been looking at Cayley graphs. So we say, okay, let's just kind of focus on cube-like graph. So we just focus on that special Sylvester type Hadamard matrix. And so Sophia came up with, like she answered this question, and the answer is yes. For cube-like graph, it's possible to have more than two vertices that are pairwise strongly cospectral. And basically she came up with these very pretty drawing of graphs. I really like these drawings. I think they're very pretty, so I couldn't resist and put down two drawings there. I would fill in more if I have more space. Okay, so Sophia not only find examples that you can have more than two vertices that are pairwise strongly cospectral. She showed that basically these vertices would form an elementary 2 group, so they can come in either 2, 4, any powers of 2. So now that we know that it's possible, my next question is for cube-like graph. For those graphs with, say, 4 pairwise strongly cospectral vertices or 8, can we characterize connection set? Can we tell from the connection set when a graph would have, say, exactly 4 pairwise strongly cospectral vertices? I'm curious about this because I guess back in my mind, I was thinking about this result by Chris in 2011 with his URA Zheng. Basically, they look at a cube-like graph that has perfect state transfer at time pi over 2 and pi over 4. And they look at basically a linear code that you can construct from the connection set. And they can characterize basically if a cube-like graph will have perfect state transfer at those 2 times using properties of the code. So there's a coding theory connection to it. So there's another reason, like in the back of my mind, I find this kind of interesting. Okay, so for the next few slides, I'm just going to kind of give you the story of what happened in the last few years. So I learned about fractional revival in Canada in 2017. So Luke make a very brief stop at Toronto, and he gave a talk in fractional revival. That's how I learned about it. Before that, for like the previous kind of 15 years or so, many people have studied perfect state transfer. So Gabriel, Chris, they spent a lot of time studying perfect state transfer, Tino and Harmony. And I remember, like in Canada, I remember kind of learning this definition of fractional revival. And I think, okay, the two definitions are really, really similar. I mean, you basically have almost the same ingredients. You have your transition matrix, you're talking about the graph, you're talking about two vertices, you have vertex A and vertex B. Okay? And the only thing that's different is you kind of sneak in an extra parameter. So you have a little, like one more degree of freedom, just a little bit kind of freedom that you allow in fractional revival. So I was really curious because I thought, okay, so we have almost the same ingredient. We have this extra kind of parameter. So how is fractional revival different from perfect state transfer? Now, we know that perfect state transfer are rare. There aren't that many graphs with perfect state transfer. So with this kind of extra degree of freedom, does it mean that we can have more graphs, a lot more graphs with fractional revival? And I remember kind of bugging Tino and Gabriel and Harmony with this question. And I remember in Delaware in 2017, we all kind of crowded in a dorm room, and we sat around and we talked about this. It was fun time. Now, one of the questions that Tino raised is that we know that perfect state transfer is monogamous, meaning that if a graph has perfect state transfer between from a vertex A to another vertex B, then A would not be able to have perfect state transfer to a different vertex. Okay, so if perfect state transfer happens from A to another vertex, then that's it. Okay, so it's monogamous. So A is stuck with B essentially. So Tino's question is, well, does fractional revival have to be monogamous, or can it be polygamous? So if you have attended Xiaohong's talk, then you know the answer. Okay. So this is 2017. Now in 2018, we met Whitney and Mark and Gabor in the AMS meeting in Boston. I've never met Or Eisenberg in person. And then that meeting was followed right after by the quantum walk workshop at Waterloo. So it was very intense 7 days where we talked about quantum walks. It was a lot of fun. And then a few months later, they show us this graph. So they show us this 4x4 graph. It's a weighted graph. Okay? But then they show us that this graph has fractional revival from the vertex, the second vertex, to basically any other vertex at different times. Okay? So we have our first example of a graph, a weighted graph, to show us that fractional revival can be polygamous. So U2 has fractional revival to all the other vertices. And this example, if you look at this example, it's a Hadamard diagonalizable graph. Okay. So we have this 4x4 example towards, I guess, the end of 2018. Okay, and then a year went by, time flies. This is right before the CMS meeting in Toronto. Tino came in a couple of days earlier. We're just hanging out at York. And then we're looking at this example. We're basically we spent an afternoon staring at this example, trying to understand it. And then we figured that their construction, and I'll show you what they do in this, what the construction is really about, actually works for any Hadamard matrix. So I'm sorry I squeezed in a lot of stuff in this slide, but the way it works better if I have all the information on the same slide. Okay. So to construct a Hadamard diagonalizable graph, we need the eigenvectors. So we need to basically pick our Hadamard matrix. We need the eigenvalues for the Laplacian matrix. So we need to pick the lambdas. And then once we have these two sets of ingredients, then we can just basically compute the Laplacian matrix. Okay. So in this example, I pick this matrix, this Hadamard matrix. So this is the character table of set 2 square. Okay, so I know that well, you don't have to pick a character table for set 2 to the m, but in this example, I'm going to pick this. So because I picked this to be my Hadamard matrix, I know that whatever graph I get at the end will be a Cayley graph, or it's a vertex transitive graph. So I have my eigenvectors now. Now I need to pick the eigenvalue. Okay? We are dealing with the Laplacian matrix, so we know that one of the eigenvalue corresponds to the first column, is always 0. Okay, so that is a simple, that's easy. Now then for the other 3 columns, then what we do is we set up 3 systems of equation. Okay, so we want to deal with modular equations. We're going to use the Chinese remainder theorem. So we pick 3 distinct primes. Okay. Now, all you really have to do is to pick 3 numbers that are relatively prime to each other. So let's just pick 3, 5, and 7. Okay. And then the way I set up these system of equations is I look at the entries of the column. So for lambda 2, I'm looking at column 2. Okay, so if so for row 2, I'm gonna look at mod P2, P1. Row 3, I'm gonna look at mod P2, and row 4, I'm looking at mod P3. And then what I do is I look at the entries.
Just checking in, we should probably wrap up soon. So if you want to, I mean, we can obviously go on after questions.
Yes. Okay. So I'll just finish this part and then I'll stop. Okay. And then so what we do is we look at the entries. If I see a -1, then I'll put a 1 here. If I see a 1, I put a 0 here. So we have 3 system equation. We solve it. We get our eigenvalues. Okay. And then we compute the Laplacian matrix. Okay. And what happens is that in this Laplacian matrix, if you start with any Hadamard matrix, then the vertex 1 will have fractional revival to any other vertex at time 2 pi over pi. Okay. And because this graph is vertex transitive, so what happens is that in this graph, we'll have fractional revival between every pair of vertices. Okay. And this is also an example of a graph where basically all the vertices are strongly cospectral with each other, but it's a weighted graph. Okay. And this is the last slide. So then, of course, the next question is what happened to the unweighted graph? And so Xiaohong and Chris were looking at fractional cospectral vertices in this summer. And then so Xiaohong come up with a family of graphs. This is one example of it, where the adjacency walk will have fractional revival that are polygamous. Okay? And then in the summer, Harmony and I had the pleasure to work with 4 very strong students in the Fute URA program. And August, one of them, he came up with an example of a regular graph that basically we have fractional revival that is polygamous. And these graphs are in the scheme, so it works for both adjacency and Laplacian. Okay. And then, so I finished 2 out of 3 parts of the talk, and then maybe we can talk about this on a different day. Okay. And that's it.
I think we'll have to. All right.
I'm going to show you the last slide, though. I have to show you the last slide. So I want to finish by saying stay safe in 2021.
Thank you. Thanks, Ada. All right. Do we have questions? I suppose I can start. I was wondering if there are, because you mentioned at the start that you wanted to think about the sort of most general version of complex Hadamard matrices, where you allowed just any complex number with norm 1. Are there examples where you use where the Hadamard matrices you're using to diagonalize the graphs are these sort of wildest possible ones, or do they typically end up being these sort of like character table type things? Or
well, I mean, if you take any complex Hadamard matrix, right, then it will diagonalize the complete graph.
Right.
Right. But so we actually try to look at the Button type complex Hadamard matrix. For example, the cycles are examples. But then in those graphs we can't we won't be able to say as much about the eigenvalues, because let's say if you take the cycle, then you only have one integer eigenvalue. So we were able to say a bit more if each entry is a pth root of unity. But other than that, outside that, then we couldn't say a whole lot. And for example, like we don't even know of the 6x6 complex Hadamard matrix. So it would become like quite difficult. Yeah.
I guess you don't buy yourself more freedom by like it gets too wild to know what you're looking for, I guess, if you.
Yeah. So so we are kind of stuck at that point. But my real motivation is really type 2 matrix of Hadamard matrix. So I really want to go back to the Hadamard matrix part. Yes.
Other questions?
Can you just quickly go over what was the last part of your talk?
Oh, okay. So what happened is when we compute the Nomura algebra of a type 2 matrix. So let's say I want to look at the Hadamard matrix. So I want to compute the Nomura algebra of the Hadamard matrix. And what happened is, one way to think of it is we can think of taking my Hadamard matrix, okay, and I can normalize each column. So I actually am dealing with n different Hadamard matrices if I normalize each column. So I can just basically scale the rows to make a different column being the vector of all ones. So I'm talking about n different Hadamard matrices, although they're equivalent. Okay. Now then remember the set S that I was talking about. So I would have a set S for each of these Hadamard matrix. And then what happened is if you take the intersection of these set S, then that's the Nomura algebra. And the problem is, Jaeger, Matsumoto, and Nomura, they show that if the size is congruent to 4 mod 8, there's a very simple counting argument that says that the Nomura algebra, this intersection, is the span of I and J. Okay? And this Nomura algebra is always a Bose-Messer algebra of some association scheme. But then we don't know what happened when the size is it's a multiple of 8. Now, Chris had a URA a long time ago who did some computation up to size 24, and the Nomura algebra is always basically a product of smaller schemes, like the smaller trivial schemes. So the question now is like, if you look at size congruent to 0 mod 8, is it possible to have a Hadamard matrix that would have a Nomura algebra that is non-trivial and it's primitive, that is not a product? So that is the question that I'm curious. And Nomura algebra, it's really interesting because they come in dual pairs, because you have W, you have the matrix H and H transpose. And also, if the type 2 matrix belongs to its own Nomura algebra, then you have what we call spin model. So you get link invariant. So there's something very interesting going on that part.
Okay.
So what happened is, like, now we know a bit more about the structure of these graphs. I'm stuck. I don't know how to kind of, I haven't really had time to kind of think about, okay, what can we say about the Nomura algebra of these Hadamard matrices?
Has anybody looked at the Hadamards on 32 yet?
No, not yet. I have this program in my computer at work that so now all the Hadamard matrices of size 32 are classified. So I guess the next step is to kind of run through them.
Yeah, they weren't classified when we did our stuff, so we couldn't do 32.
Yeah. So that's.
And I'm not confident that there'll be anything on 32 because you would expect to get a strongly regular graph, and there's no strongly regular graphs on 32 vertices that aren't in primitive.
Yeah.
So
that's why I'm hoping, like,
case.
I'm hoping we can get some information. Like, we know that we have all these equitable partition, right? So we have not just n-1, we actually have more because we have kind of these n different Hadamard matrices do it. So we have tons and tons of equitable partition. So I'm just curious at what more can we say given this structure? So we know a bit more about these graphs now. But well, in my last slide, I show that like basically 2022, last 10 months just vanished because everyone's studying at home or working from home and then teaching online. Like it's just been crazy. So if any one of you are interested in working on this problem, I'll be excited to basically talk to you guys about it. Yeah.
Great. Well, let us thank Ada again.
Thank you.
And we will hopefully see you all next week.